Hello, and thank you for attending today's webinar, Enabling Closed-Loop Assurance Through Real-Time Analytics, featuring EXFO. I'm Scott St. John, Managing Editor of Pipeline Magazine, and I'll be the moderator of today's webinar. Joining us today is Jose Anez from EXFO, a leading provider of next-generation testing and assurance solutions for wireline and wireless networks. On today's webinar, we'll be exploring ways to transform the legacy assurance process by leveraging real-time analytics for faster decision-making and time to resolution. As networks continue to evolve and customer expectations continue to rise, service quality becomes increasingly important. We are very glad to have EXFO join us today to discuss this very important topic. As a quick reminder before we begin, you can submit your questions in the Q&A window in the lower left corner of your screen at any time during this webinar. Even if you're viewing this webinar on demand, you can still submit your questions using the Q&A function, and the presenter will reply with an answer. We encourage you to submit any and all questions you might have to be addressed at the end of this session. With that, let's jump right in. Hello, Jose.
Hi, everyone. Thank you for joining. Today, we will define and show you the importance of having a closed-loop service assurance and a closed-loop analytics system to manage your network environment. We are focusing on network function virtualization, but this applies to legacy physical networks and to software-defined networks. We will tell you about what we consider the best practices for building a closed-loop analytics system. We will tell you what we consider are the system requirements for such a system. And at the end, we will explain why you should be choosing the EXFO XTRACT analytics platform to do your closed-loop service assurance analytics. A good closed-loop or closed feedback loop management system will go like this. You will have a service implemented, typically by your orchestrator, and the system will be collecting data on a very continuous and very frequent way. That data collected will be fed into the service model, a representation of how your service is built, how it impacts, and how it performs. The management system should be able to do analytics based on the model and based on the data collected. And based on those determinations made by the analytics system, it should be able to make a recommendation of any change that needs to be done to improve or fix service quality issues you have in your network. The part that makes it a closed loop is that once you produce those recommendations and they are implemented again by the orchestrator, in the case of a network function virtualization system, or maybe manually in the case of a traditional legacy network, the system should continue collecting the data, applying the same models, and validating that the recommended change has taken the effect that it was expecting, or maybe provide future recommendations for an even better service quality. So in a summary, a closed-loop service assurance is continuously measuring the performance of your network, computing the service quality. It could be a service quality index, a customer experience index, or some other key quality indicator that measures the experience your customers are going through. It should compare that to the expected performance and expected service quality, and then it should issue recommendations. Those recommendations should be implemented by either the NFV orchestrator or the operator, and it continuously measures it again and keeps computing it. You probably have seen these numbers, but it's really important to see them again. Many service level agreements are based on several nines of availability, 99, 90.9, maybe even 5 nines of availability. it is always important to recognize that when we are talking about 5 nines of availability, you have less of a minute of downtime in your environment. Even if you go with less stringent availability contracts, you're only talking about minutes in a month that you can have a downtime. Take a look at those numbers. On a very typical 99.9 environment, you have 43 minutes of unavailability that you can tolerate. On a 99.99, 4 minutes of unavailability. That puts into perspective the importance of real time.
Jose, I think this is really important. SLAs are critical to the customer experience, and not meeting them can lead to costly penalties and churn. What you're saying here is, in the end, the difference comes down to a matter of seconds between complying and not complying with your service level agreements.
That's correct. And most carriers, they are held accountable to service level agreements. And most application providers, even internally within an organization, are held accountable to some level of availability. The same calculations can be made to agreements about service quality indexes, and you will find that the tolerance numbers are probably in the same level of magnitude. By now, most companies or more network operators have a management environment, and it typically has the components shown on the screen. It is very typical to have fault management, which will address alerts and alarms generated by devices themselves. Those are typically received in a very short time frame, almost real time, but then it lacks the context that is provided by a performance management system. For example, it can have the indication that an interface has gone down, but it lacks the history of has it gone down in the past, or has it been overutilized, or has it shown an excessive amount of errors or packet loss or any other indicator. And then all of the information being collected out of the different components of a service, it typically is out of context if you don't have some kind of service level manager that will show you how the device behavior and performance is impacting the actual availability, maybe the service quality, the delays or response times, the failed transactions, or any other measure that is used to calculate the service quality index. Typically, all of these components collect data independently and in separate ways, and then they have to be correlated, analyzed, maybe even shown in a manager of manager. And all of that has to happen before we can start doing corrective action. As you can imagine, the typical collection frequency for these systems is in the 5 to 15 minute range. By the time an accurate correlation and analysis has been performed, 45 minutes may have gone by, and that starts to show that even a single performance degradation or outage will, first of all, take you out of compliance of the most common service level agreements, and certainly the mean time to repair will be impacted, and maybe you will even have a minimum of, let's say, 30 to 45 minutes of mean time to repair, which is dramatically high in today's environments, especially when we are moving to very dynamic virtualized environments. You can combine that by recognizing that those systems that we've mentioned, fault, performance, service level, and then correlation and manager of managers, those may also be subdivided across multiple domains: application management, systems management, network management. That increases the delay to reach an accurate representation of your service quality and the impact to your service customers. The complex correlation rules make it error-prone, and is just the fact that you are bringing data from multiple disparate systems will increase time misalignments, so that it will impact your ability to correlate data on the same time scale. This is significantly important now that we are moving into virtualized environments where the computing power being used for network and systems, and obviously the applications running on them, may be shared. You need to have a system that is ready for the new virtualized era, where all of these components are sharing resources, and the whatever impacts the network may eventually impact the systems providing your applications.
Jose, you're mentioning virtualization technologies and how they're providing more visibility and control. Can you go into that a little bit more and how that impacts closed-loop assurance?
Yeah, absolutely. So right now we are moving into an era where your network and your systems, and of course the applications that you're offering to your customers on those systems, are essentially on the same physical infrastructure, on the same hardware. Any impact that you get on your network is affecting your ability to provide the compute power you need as well. Let's think about the objectives of real-time analytics and as they affect a closed-loop service assurance system. You want to have the lowest mean time to repair you can have, and everything you measure tends to improve. It is typical you are measuring mean time to repair. You want it to go below a large number, such as 30 minutes or 45 minutes that you can experience on typical service assurance applications. You want it to be able to reach the minute, less than a minute, or approach zero, essentially. Can only be done with a very real-time system. You want this to be a very efficient operation where you eliminate blocks, you eliminate bottlenecks, and you eliminate anything that will prevent you from reducing that mean time to repair. You want it to be in absolute real time as things are detected, as things are happening. And you want, or the most important thing you want the concept of a small change delta for continuous improvement. And that's one benefit you get if you are on a really real-time environment. Let's talk about the smaller change delta for a moment. In the current slide, you see what may be happening on a large delta, low change frequency environment. Let's take a look at this graph. You're detecting a packet loss, some percentage of unacceptable packet loss. Your system is collecting, let's say, at a frequency of 15 minutes. By the time you detect that you are offering a lower service quality to your customers, you take corrective action. You essentially recommend increasing bandwidth, and you increase the bandwidth. Since you have 15 more minutes to get to the next measurement, the typical recommendation will request a very high increase because you want to be done with this problem for once and for all. This results in waste of resources. Now think about it. In a virtualized environment, your network is sharing physical hardware that is being used or could potentially be used by other systems, other applications, other services being offered to your customers. More importantly, it's not only the network. these servers that run the applications themselves may be sharing infrastructure. So every resource you take away is a resource that will not be used by another application that may need it in this moment where your company is going through a higher level of utilization. Also, since you have a larger data collection delta, you essentially have one chance to fix this for once and for all. You better offer the right recommendation, and you better offer a recommendation that is large enough to fix the issue. That's a very tall order, and it results in overcompensation. It may even result in the wrong suggestion. At the end of the day, this low frequency of change results in a large mean time to repair. Now let's take a different approach. Let's look at how we believe you can have a closed loop service assurance management system. On a closed feedback loop, you detect the same level of packet loss, but you are collecting at a very small delta. Let's say you are collecting every minute. To detect the packet loss, you offer a recommendation. You offer the recommendation to increase bandwidth by some amount, a smaller amount than in the previous example, because you know that in the next minute, after the recommendation has been executed, you will be able to validate if the approach is the right approach, if increasing bandwidth indeed starts to improve the situation. Otherwise, you will be able to offer a different recommendation. 1 minute goes by, you detect that yes, indeed, increasing bandwidth improves the situation. You still detect some level of reduced, but still existent packet loss. We issue the recommendation again, increase bandwidth by another delta, and so on until you detect the issue goes away. Now let's see the benefits. This is efficient. You may not have wasted resources that were available to other systems. You were verifying that your recommendation was the right approach. Otherwise, you would have offered a different approach next time. And obviously, you got a smaller mean time to repair by doing high frequency changes given a very small delta polling. You were making very small incremental adjustments at a very frequent pace. That is perfect for the concept of a closed feedback loop service assurance that is needed in network function virtualization environments. Other characteristics of real-time closed feedback loop management systems include eliminating as many bottlenecks as you have. A very typical bottleneck in management is I/O, or the time it takes to get data that you have collected into a management database or getting it out of the database for analysis. A real-time system should try to keep all of the data that is needed for real-time analytics right there in memory for a sufficient time to be able to make a recommendation. It should keep baseline so that it can detect how things are deviating from normal so that it can issue a recommendation to correct so that that deviation doesn't continue, so that you don't get service unavailability in the near future. That means you have a system that may have prevented downtime or service degradation before it even started because you were keeping track of it in memory. You were using a live baseline. You were looking at deviations from what is the normal behavior, and you were starting recommendations to bring it back to normal. At the same time, of course, you need a system that stores data for the longer term. That data will be used for longer term baselines, for example, obviously. And that system will also store data for longer term analysis and longer term capacity planning. And all of that is fine, but you have to make it in an efficient way that also takes advantage of modern systems. Systems that have a low cost of memory, low cost of compute power, but you still have a very high cost, at least time-wise, time spent in storage I/O, in getting things in and out of a database. Some of the benefits you get from in-memory service assurance. You can run all of the data you're collecting live in microseconds through the service model. The service model can be looking for key quality indicators that combine multiple key performance indicators you collect from the service components, apply service models, and come up with a service quality index. In real time, it is shown, it is alarmed, it is measured in sub-seconds after data is collected. That is key to being able to make recommendations almost as soon as you collect the data. In-memory analysis also allows you to run the same data you are collecting through topology and doing a root cause, downstream suppression, and any other advanced analytics you can use on the topology model that you have, and being able to determine impact to the other service components, being able to know that this device that is starting to perform incorrectly will start to impact a different device or the service offered by a different device in the next 10 minutes. And you can start making recommendations to avoid degradations on the other system. Or it will impact those customers. And you can start making recommendations to take mitigation actions to service those customers. Maybe add more hardware, maybe add more virtualized systems. It also allows you to, in real time, keep a multi-dimensional correlation of the multiple technology domains, such as databases, systems, networks, applications. All of these management systems, especially those in a closed feedback loop system, need to integrate with third-party tools. The obvious integration point is the orchestrator. You need to feed a model from this orchestrator into the management system. You need to feed back recommendations about what actions to take to improve service quality to the orchestrator. And you need to be able to receive feedback from the orchestrator on both if the changes that you recommended were made and if they were made, if they were effective. So it is important that you provide an API that can be used for both collecting and also making available data for others to use. It needs to feed directly from the analytics platform, and that means feeding directly from the in-memory database where the alarms are generated in real time. It is also important that these real-time APIs provide microservices that can be incorporated into the workflow of those performing the work and keeping the networks highly available. It is important that any workflow that the management customer has, or any tools that they use, any visualizations they have in their network operations center, can show the data that is being analyzed in real time as soon as it is being collected. And most importantly, if you want to provide closed-loop service assurance or closed feedback loop service assurance, you need to base it on the service itself. You need a very good service model that continuously calculates the quality indexes at the multiple levels of the service, be it the different providers of the service, the different regions, geographies, components and subcomponents, redundancy considerations, high availability considerations, capacity considerations. All of that has to be modeled into quality indexes, and you needed to be able to pinpoint naturally where the source of the degradation of the service is, and to pinpoint which service customers will be impacted by that degradation, so that you know where you need to go and take action first. Other important strategies for an optimized closed-loop service assurance system is you need to be able to store data in the way you retrieve it. You need to be able to take advantage of all of the hardware improvements we had over the years and compensate for the I/O cost, so that you can be able to bring in and out of the database massive amounts of data. And you need to be able to distribute the load across multiple systems. Now let's summarize the characteristics of a real-time closed feedback loop analytics system. First of all, it needs to be fast. It needs to be real-time. 1 minute data collection frequency and analytics is preferable. Faster is even more preferable, of course, it will impact performance. The 5 or 15 or 30-minute industry standards are not acceptable for real time. Real time needs to approach now. It needs to be low latency. It needs to take advantage of fast processing in memory. Data that is going to be processed needs to go directly into memory, analyzed right there, combined with short-term baselines with predictive analytics that let us know when things will start to degrade, and that allow the system to start making recommendations on what needs to be changed to be able to prevent the actual failures. And that needs to happen, of course, in real time. The most frequent you collect the data, the better. You need to make incremental changes. Those incremental changes help you in multiple ways. It optimizes resource use that protects other systems. It allows the analytics system to validate that the recommendation was the right recommendation, the right approach, and that it should continue going that path. And if it cannot validate that, it should start a secondary option, a third option, until it finds the way to correct the situation. And it needs to be end-to-end, really end-to-end. You want to minimize the correlation of data between multiple systems. You don't want to normalize across different timescales, across different KPIs, across different ways to measure quality. You need to be able to manage things in an end-to-end system that understands all of the layers, that understands the subscriber, the actual end user, that understands the services being offered and what affects the quality of an application and the user experience, and that understands the actual network infrastructure being used to provide those services. Fortunately, there is an application that was designed with those ideas in mind. When EXFO XTRACT was designed, it was designed for real-time analytics and for real-time recommendations. We are fortunate that we did that, because now with the network function virtualization technologies that are being developed, it fits perfectly in that schema. It is a system that allows you to manage the subscriber, the service, and the network on which your application depends. It is a system that can provide real-time analytics in a very frequent basis, a system that has a very advanced alarming system that progressively issues recommendations and validates that those recommendations were effective at improving your service quality. It is a system that takes advantage of the vast amount of memory and processing power we have in current systems, and those in-memory baselining, in-memory alarming, in-memory recommendations provides that through an API and through its own interfaces. And then it scales on top of that horizontally and vertically. It scales at levels that are up to 20 times what many of our competitors do on a single system, and it scales horizontally, so you can have multiple systems sharing the load. By default, it does 1 minute data collection, while many of the competitors do 5, 15, 30 minutes. And that allows you to collect data very frequently, analyze it equally frequently, provide recommendations, and next minute you will have feedback on how well the recommendation was able to take corrective action. And if it did, you can keep doing more of the same, or if it didn't, you can take the secondary, tertiary, or further actions to fix the situation. It was built, or XTRACT was built with an advanced service modeler, essentially something that you can use to model your service components, your areas, your geographies, your dependencies, how you build it, your redundancy and high availability options, and it allows you to propagate service quality indexes and customer experience indexes all through the service model so that you can figure out what is impacting or what portion of the model is impacting your service quality or what customers are being affected by the service degradation. And you can prioritize change. So XTRACT is the best approach that you may have for building a closed feedback loop service management system in a network function virtualization environment or in a traditional network environment. Thank you for joining us. I'm available now to answer any questions.
Thank you, Jose, for sharing your insights on best practices and how to leverage real-time analytics for closed-loop service assurance. It's truly an innovative approach to ensuring SLA and service quality are efficiently maintained and service degradations are addressed as quickly as possible. We received some great questions from the audience. Please keep sending them in. You can just use your Q&A panel on your screen, and we'll get to as many of them as we can. Also, I wanted to let everyone know that there's a white paper available on this topic. It's available for download through the webinar platform under the handouts icon at the bottom of your screen. Okay, the first question is for you, Jose. How is in-memory database, or what is the impact of in-memory database? I know you mentioned cost being a key factor, but are there other areas of impact?
Absolutely. There is an impact by keeping the data that we collect in memory for about an hour. We have found that for systems that are collecting data on 1 million elements, and when I say 1 million elements, I refer to things like network interfaces with around 30 KPIs each. When we're collecting data for 1 million elements, we consume around 20 gigabytes of RAM, and it can perform adequately. So while we do believe that there is a cost in memory, memory is cheaper nowadays, and more importantly, when you account for the benefit you get about the in-memory database, the really fast and real-time calculations and analytics you can perform on it, compared to the very slow time it takes to storage, input and output, it more than outweighs the cost of memory.
Excellent. So in addition to the low cost of memory, we also have speed as a key factor. This one's somewhat related. Is 1 to 2 minutes mean time to repair actually achievable, and are you seeing that from your customers?
Absolutely, we are seeing it. We may be seeing something better than 1 to 2 minute mean time to repair. It is just that most customers do not account for, let's say, 0 time to repair. And let me explain that. By having an in-memory baseline and by continuously analyzing the performance of your network, we can alert you of impending performance degradations or availability or unavailability situations before they happen, before you actually incur into unavailability and you start the counter for mean time to repair. And even if the failure do occur, if you had, let's say, 5 or 10 minutes of advance notice that it was about to fail, yeah, you can certainly get to that 1 to 2 minute mean time to repair.
Excellent. Thanks, Jose. The next question is, and this is even somewhat related to what you're talking about, collecting that real-time data and being able to action that information more quickly. Are you afraid of making the wrong recommendation? If you're making semi-automated recommendations and actions to correct a problem, how is that? Are you ever afraid of that recommendation being wrong?
A few things here. So first of all, most of the time, the recommendation is based on the knowledge of people operating the network, people who know how to react to these situations. So more often than not, the recommendation is actually the right recommendation. Now, occasionally, yes, it is possible that an automated recommendation is the wrong one. The reason we are not that afraid of doing that is because we are collecting data and we are making recommendations in near real time, let's say every minute or so. So if we decide that we have taken a recommendation that doesn't help mitigate the performance degradation, there is always another minute to try a different course of action. And since we are in a closed feedback loop where we do a very small incremental change, figure out if it actually helps the situation, and if it doesn't, we issue a different recommendation. We are actually improving upon the traditional method of just trying something drastic to see if it fixes it. So if we try a recommendation on minute number 1 and it doesn't work, and we try a second recommendation on minute number 2 and it actually works, we are still way ahead from traditional management systems that need to make a huge recommendation in a 5 or 15 minute delay window.
Right. So by making smaller incremental changes more frequently, you can see if it's actually impacting and addressing the issue, as opposed to waiting longer periods of time and having to make larger, more significant changes.
Absolutely, yes.
Okay, the next question has to do with network virtualization, and it's asking, I know you talked about NFV a little bit earlier, but how is virtualization technology impacting the service assurance process overall?
It is impacting it in the sense that the network and the infrastructure you're using are continuously changing. And you need to continuously monitor and adjust the service model and the topology to the current reality. You also need to keep track and understand if those changes were part of the new way of performing. If you use a tool like XTRACT that keeps an accurate, up-to-date, up-to-the-minute topology and up-to-the-minute service model, you're more likely to be able to make accurate recommendations on what changes are needed. Traditional service assurance tools may not be capable of doing up-to-the-minute service model updates or topology changes to make the correct recommendation.
Thank you, Jose. That's all the questions we're going to have time for today. We'll continue to review and answer any remaining questions after today's call. Thanks again to our presenter, Jose from EXFO, and to all of you for attending today. We look forward to seeing you all on the next KnowledgeCast webinar.
Thank you.